Welcome back to lecture. And this lesson is a continuation of our algebra review. This is lesson 2, so let's get started. I'll move myself down here for a second. Exponents. What about exponents? Exponents are how many times we're multiplying a number. We saw this briefly last time. Or variable by itself. So 4 cubed, I've got a number. This is just a shorthand way of saying I want to multiply 4 by itself 3 times. So 4 cubed is just 4 times 4 times 4. If I have a variable, I'm writing it the very same way. I'm saying x to the 5th. This is shorthand for saying x times x times x times x times x. Multiply x by itself 5 times. Now, if we multiply two numbers with exponents together, all we have to do is just add the exponents. Now, the variable or the base here has to agree. So here's an x, here's an x. Now, I had 2 of them from here, x times x. I have 3 of them here. They all match. So let's just do the shorthand. X, 1, 2, 3, 4, 5. I just write it as x to the 5th. All I have to do is just add the exponents. So x to the m times x to the n is just x to the m plus n. If I divide with when I'm using exponents, all I have to do is just cancel the common factors in both the top and the bottom, or just subtract exponents. So this is shorthand of saying x to the 5th. There's x multiply itself 5 times. Divide by x squared. I'm doing my x times my x. 2 of these are going to cancel. I'm just left with the x cubed, or I can do the subtraction rule that just says if I'm dividing, all I do is subtract the exponents. X to the 5th minus 2, which is just x cubed. And this is just like simplifying with fractions. So if I had 5 times 5 times 5 times 3 and a 3 times a 5, I'm going to do common factors. That 5 and the 3, 3 and the 5, all I'm left with is my 5 times 5, or 25. What about if I end up with a 0 exponent? I've divided, let's say, x cubed divided by x cubed, so I did the subtraction rule, x to the 3 minus 3. I end up with a 0. That just means that all the factors have canceled, and I'm left with 1. So every time I cancel a factor, that's really I replace it with 1. And b to the 0 then is just 1. 5,000 to the 0 is 1. Negative 3x, that means everything in this parentheses is 0. Raised to the 0 power, that's just 1. And that's for all numbers as long as x is not equal to 0. 0 to the 0 is not 1. If I have a negative exponent, here's different ways that I could write this. B to the negative n is the same thing as 1 over b to the n. And if I have top and bottom with the exponents, that's 1 to the n divided by b to the n. And 1 to the n is just 1. 1 to any power is just 1. Okay. So 4 to the negative 1, here's some examples. I'm going to write this 4 to the negative 1 as 1/4 to the 1, which is 1/4. If I have a negative exponent, I'm just writing it down to the bottom. X to the negative 3, 1 over x to the 3rd, which is 1 over x to the 3rd power in the denominator. So I can move an exponent, a negative exponent, to the bottom. And if I had a negative exponent at the bottom, I could move it up. I just flip it. So let's look at some exponent simplifications. Here's just some examples of some of the things that we've talked about so far. I want to multiply b to the 4th times b squared. There's my 4 of these, 2 of these. So how many have I got? 4 plus 2 gives me b to the 6th. So b to the m times b to the n is just b to the m plus n. There's our quick little rule. If I've got b to the 0 times b to the 3, b to the 0 is just 1. 0 plus 3 is still just b to the 3. B to the 3rd power. Okay. So here, simplify these. I'm going to go over them. 8 to the 0, anything to the 0 power, I can replace with 1. Here I've got negative 8 to the 0. That 0 is only concerned with this 8 itself. I still have to have this negative 1 out front. If I wanted everything, I'd have to put a parentheses, and raise that to the 0. So here my negative 1's out front, 8 to the 0 is just 1. So this is negative 1. 8 times x to the 0, that's just 8 times 1 is 8. 8x, here's the parentheses, so it's everything in here raised to the 0 power, and that's just my 1. Okay. So here I'm multiplying 2, b to the negative 3 times b to the third. When I get b to the negative 3, if I just add the exponents, negative 3 plus 3, that gives me b to the 0, which is 1. And if I go back and if I rewrite b to the negative 3 as 1 over b to the third times b to the third, all of these cancels, and I should have the 1. Okay, so there's our rule, b to the negative n is just 1 over b to the n. Here the negative exponent, 1 over q negative 2, is in the bottom. So this is 1 over q squared, and when I divide a fraction, 1 over 1 divided by 1 over q squared, fraction divided by fraction, I invert and multiply. I invert the 1 over q squared to give me the q squared over 1, so that's just the q squared. Q to the negative 2, 1 over q squared, 1 over q to the negative 2, q squared. I just move that up top. This goes down to the bottom, and I can change the sign. So here I just want to represent this as all positive exponents. So I just represent 5p to the third. This is not anything common, so I can't do any cancellations here. I can't add the exponents, but I can take this q to the negative 2 and put it in the denominator. Numerator, 5p to the third, denominator, q squared. So here's just a similar problem. Now I've got 5q squared up top. The p to the negative third goes to p to the third. So here's the rules that for exponents that you need to keep in mind, kind of make you some flashcards. Product rule for exponents, anytime I multiply the same base, different exponents, I'm just adding the exponents. They could be the same, but I still add them together. And here's the example. If I divide, I subtract take the top and subtract the number out of the bottom. These are all that's canceled. So it's just b to the m minus n. And here's the power rule. So if I have something raised to inside, I've got b to the m. And this could be across factors as well. This raised to this power, I've got b to the m of them. How many times do I multiply that together is n times. So I have b to the m times n. I just multiply these exponents. And here, even with negative exponents, it works. So negative 2 times 3, y to the negative 6, because I'm inverting all of those. The power of a product. So if I have AB here, I expand that as saying A to the M, B to the M, and I can mix these with here. If one of these was raised to some other power, I would multiply that times that, whatever that exponent would be. So here's an example. 4x raised to the fifth is just the 4 to the fifth, x to the fifth. And then power of a quotient, anytime I have the quotient, that's division, and raise it to a power, it is just the numerator raised to that power and the denominator raised to that power. So here's an example, 3 over z raised to the 8th power, that's just 3 to the 8 divided by z to the 8th. So in many applications, we're going to be dealing with large numbers or very small numbers. And when I'm doing large numbers where I have a lot of zeros that are trailing, or small numbers where I have zeros preceding the significant digits, and here is where the 2 and the 6 are significant, all these zeros I can kind of recover if I do scientific notation, so I don't really need to do those. But I can write this thing as 2.6, and then how many times did I do a multiplication times 10 here? 1, 2, 3, 4, 5, 6, 7, 8, 9. I can represent this number as 2.6 times 10 to the 9th. And I can recover it if I do the multiplication out. I still get this. So this is my significant, is the numbers preceding the zeros, and here the significance is when I first find one that is a non-zero, that 5 would be significant. So I would want the decimal place here as 5. But notice this is actually representing divisions instead of multiplications. So this would be 5, and to get that decimal, I count 1, 2, 3, 4, 5, 6 to get the decimal place there, but it would be times 10 to the negative 6. I'm actually dividing 5 by 10 to the 6 to recover that number. Okay. So very large, very small numbers. This is just a convenient way, a compact way of writing the numbers. And historically, it was easier to do multiplication division when you're dealing with very small numbers, large numbers, by representing them as power of tens, and then handling the addition of the exponents or subtraction if we were dividing. So here's just many times we'll have the answer in the back of the book that we will run into, and it'll be represented in scientific notation. So let's just get some practice. I want to represent the 29,980,000 in scientific notation. So I want to put the decimal place between the first two significant digits. This is kind of the standard place that I want to put this thing. So I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is where I would want there, and I just represent that as 10 to the 10th. So if I multiplied this back out, every time I did a 10, I would recover and multiply and move the decimal place to the right. So the size of an HIV particle is approximately 0.00001 centimeters. And again, preceding zeros, I can write them in a more compact fashion and then just represent the significant digits out front. So the significant is just that 1, and I've moved it 1, 2, 3, 4, 5. That decimal place goes over 5, and 10 to the negative 5 because I'm moving to the right. I'm actually writing all of this as a division to get that recovered. So for a test group of adult females between 18 and 20 years old, the mean blood volume was 4.2 liters. How would that look in scientific notation? The 4.2 is already significant, and I'm just representing that as 10 to the 0. 10 to the 0 is just 1, so it's just the 4.2. So this is kind of already in scientific notation, but I'm just missing that 10 to the 0 just to emphasize it. Okay. So if I'm multiplying or dividing using scientific notation, what I want to do is just multiply the significant digits. So here, historically, all I had to do is these big numbers, or multiplying big and large, was just multiply the significant digits. I just end up multiplying these and then adding the exponents for the tens. So here I'd be multiplying 10 cubed times 10 to the negative 9th. Add the exponents, I would just have 10 to the negative 6, and this multiplied out would give me the 34.4. So it kept me from having to keep up with all the zeros during the multiplication process. Here's the 34.4. I want this back into that standard scientific notation position here. So here I'm moving to the left, so I'm adding 1 to this, negative 6, negative 5 from here. Because I'm moving to the left, I'm adding a decimal place. When I was doing division using scientific notation, I take the significant digits, do that division. So here it's the 2.25 divided by the 5.0, and I'm also dividing the 10 to the 8 divided by 10 to the squared. But here I've got the same base, so I can do my exponent rule. I just subtract the exponents. Take the top, subtract the bottom. 8 minus 2, there's the 6. But I've got, from my division of the significant figures, I've got 0.45. I just need to move that over 1 to the right. So I'm going to reduce this to the 5th. So every time I subtract 1 when I'm moving to the right, add them if I go to the left. So this is really 4.5 times 10 to the 5th. So we're going to be running into roots throughout the course. So we want to go and look at how we evaluate the nth roots. So we want to do extend the definition of b to the n to expressions in which the exponent n is a rational number. Okay, so first we need to understand the relationship between nth powers and nth roots. We know that for a greater than 0, this is understood squared, so the square root of a is b if b squared is equal to a. Okay, so for other roots, for a positive integer, n greater than 1, we're just saying that the principal nth root of a denoted by this is a number b, such if I raise b to the nth power, I get a. So I can take other roots, 3rd, 4th, 5th, 6th, 7th, and 8th. Okay, this is the expression. The symbol is called the radical. The value a is called the radicand, that's underneath, and n is called the index. So here's here's using this slide. There's just different examples that we can work on. The 5th root of 32 is 2 because 2 to the 5th would go back. That's 32. When I'm doing a radical over both a numerator and the denominator, I can write this as the square root of 49 divided by the square root of 64. And again, 7/8, if I square that, I get 7 times 7, 8 times 8, and that's the 49 over 64. The cubed root, notice that this is a negative number. I can do odd roots of negative numbers and I have no problem. If I look down here at D, it says, what about the 4th root of -1? I can't do an even root of a negative number. If I multiplied even number of times, so if I raised something an even number of times, I would expect a positive number, and it wouldn't give me -1. And if I had a negative number, I raised an even number of times, I should have a positive number. So I can't do this right now. For the real numbers, we're going to have to wait until we deal with complex numbers later on to handle that. But our cubed root here is just -0.2. If I raise -0.2 to the 3rd power, -0.2 times -0.2 would give me the plus 0.04, and then the -0.2 would be the -0.008. Here's okay if I've got a -1 out front. I do the 4th root. That would be the 4th root of 1 is just 1 because 1 to the 4th is 1, and I'd still have that -1. Rational exponents also includes things where I've got fractional exponents. Fractional exponents, this thing in the bottom, that's the nth root, and here I'm going to raise that to the power. Okay, so here's just a different way I can deal with roots of a rational exponent, and this is what this means. So if I've got a to the 1 over n, that's the same thing as taking the nth root of a. So if this was the square root, this would be a to the 1/2 power. That's a rational exponent, a fractional exponent. A to the m over n is two versions of this. I can be taking the nth root of a to the m, or the nth root of a raised to the nth power. That's just two different ways of denoting that. Okay. So here, if I wanted to talk about 16 to the 3/4 power, this is the 4th root of 16, which turns out to be 2. 2 times 2 is 4, times 2 is 8, times 2 is 16. And then I would need to cube it. So 16 to the 3/4 is 8. And if I do the other way, if I take 16th cube it to the 409, and then if I take the 4th root of that, do it on my calculator, I would get 8. Okay. So here's some other properties of radicals. If n is even, if I do this, the nth root of a to the n, I'm going to get the absolute value of a. So even if a was a negative number, I raise it to an even power, that's going to turn that into a positive number. And if it was a positive, it would still be a positive. So either way, that's going to work out. If n is odd, and if I do this as whatever a is, it could be a negative number or a positive number. I could take the nth root and then raise it to the nth power. I just get my a. Okay. If I'm multiplying and I get two radicals, sometimes I want to represent this as one radical, the nth root of a times b. Sometimes I can look at this and then evaluate this easier by seeing what's underneath here. I can combine factors and see if I could actually take something out or do it. It would be like having the square root of a, square root of a. That would be the square root of, square root of 2, square root of 2, square root of 2 times 2. Well, that's just the square root of 4, which is 2. So when I bring these things in, I can actually evaluate them a little easier than just have them dangling the square root of 2 times the square root of 2. The quotient property, sometimes it is easier to find the answer if I bring both of these under one radical, maybe do that fraction, cancel out any common factors, and then represent those out. Okay. So here's an example of this. Square root of 125 over the square root of 5. I could do that equal to the square root of 125 over 5. 5 into 125 is 25, and now I can do the square root of 25, which is equal to 5. I can also nest my radicals. The nth root of the nth root of a, that's just the m times nth root of a. So here I've got an example over here. The 4th root of the cube root of x, well, that's just the 12th root of x. Okay. So many times in our book we're going to be working through and we have an answer and it's got a radical in there. We go to the back of the book and it's not going to be the very same representation that we have come up with. Well, the standard way is to look at the simplified form of a radical. Okay, and throughout the book, when they give you answers in the back of the book, this is what they're going by. They want the simplified form. Okay. The radicand has no factor other than 1 that is a perfect nth power. Okay, in other words, anything that's, if I go inside the radicand, I do a factor, I factor everything out in there, prime factorization, and anytime I have that nth power of a factor, I want to take that out. So this means that all exponents in the radicand must be less than the index. Okay. No fractions may appear in the radicand. I want to be able to rationalize the denominator and get rid of anything radicand in the bottom, only the radicand be up top. No denominator or fraction may contain a radical, that's kind of the same. The exponents in the radicand may not all share a common factor with the index. Okay. If they shared a common factor, I could take that out. Okay. So let's look at a few of these things. Multiplying and dividing radical expressions. Here's our square root of 6x times the square root of 10x. By itself, I can't do any square roots here. This is 3 times 2x, nothing. 2 times 5 times x, none of these I can take the square root of. But if I multiply them together, let's just see what we come out with. I combine them into 1. 6x times 10x, the square root of that, well, that's 60x squared. Well, now I certainly can take, here's the understood index is 2, there's an exponent 2. So the square root of the x squared I can take out as the x. I've got a 2 squared that I've combined together. When I factored this out, I can take that 2 out. Now I don't have anything. I can't take the square root of 3, the square root of 5. So I'll leave that under, and I just multiply them out as 2x times the square root of 15. And this would be the answer that you would find in the back of the book. Here I've got a radical divided by a radical, cubed root of 3x to the 7th y, the cubed root of 81xy to the 4th. I combine them. I'll look and see if I can do any simplification. I can factor out a y here or cancel a y. 3 in the 81 becomes 1 over 27. I've got an x common, so I take this out. But now I just happen that I can take out a cubed root of this. That's a 3. The cubed root of 27 is 3. 3 times 3 is 9 times 3 is the 27. Y cubed, I can take the cubed root here. Now I've got this as x to the 6, which is x to the 3 times 2. I take that out as a x squared. And I can find this out if I represent this piece of it as a rational exponent. That's 6x divided by 3, and that just simplifies to 2. So those rational exponents can also help me bring out any common, do the root of an exponent. So that's the end of our lesson 2. I hope you found it informative. We'll continue on with our algebra review in lesson 3. Have a good day.